phonon dispersion in the case of two atoms in the cell, and we were able to derive the optical modes in which atoms moving out of phase. We also just discussed the case for 3D, how it can look like. We talked about the modes in which atoms are moving along the direction of the k-vector propagation, calling them longitudinal modes, and the ones opposite, transverse modes. Putra, you know, I mean, you managed to catch up. So what are the similarities between the energy dispersion and the dispersion of phonons? Have you thought of it? Because many things we actually encountered were similar in solving, in approaching. We are plotting in the same brilliance zone. Have you had time to think about it?
Question.
I mean, what are the similarities and what is different between phonon dispersion and energy dispersion? You are plotting frequency versus k, energy versus k. Of course, they mean different things.
Isn't it that the energy can be written as a function in terms of frequency, h followed by omega?
Yeah, okay. Now I have chalk. Yeah, but it's a different kind of energy. So we have been plotting last two lectures, frequency versus k. And before we plotted the energy of the bands as energy versus k in the brilliance zone. Well, they are both working in the same k space in the brilliance zone. No? One is describing the energy, one is describing the energy, if you want, frequency of the vibrations of atoms, electronic and atomic degrees of motion. No? Different main players. So they're both periodic. You can write for any k and just translate by the g vector. They have the symmetries of the lattice, including the time symmetry, for which omega of k is equal omega of minus k. Of course, the k values are finite, but there is one huge difference. For the energy, we had an infinite number of bands. We were writing the index n, and n was infinite, because you could always describe a band, even if empty. It was endless. What about the phonons? Yesterday we derived the number of phonon modes, which is equal.
So by infinite bands in electronics, we mean the free electron model, right?
Anything.
For tight binding.
Okay, tight binding is limited by the approximation. If you use two-way functions, atomic functions in the beginning, you cannot get more.
Yeah.
But if you put more, of course, I mean, it's just a method. But in general, there is nothing which limits the upper bound, the number of bands. Is equal to number of dimensions times the number of atoms in the unit cell. So here we know exactly how many there are. This is also coming from the fact that these are bosons, so they can all go to the lowest energy state. We can have them all in the lowest state. But these are fermions.
Isn't it, I mean, for E to K, it's like infinite many paths that you can produce since you have
Yes.
you have an infinite line of sides. For the number
But
of
they're working on the same space.
Yeah.
This is not the difference. It's really the value that you are plotting. the quantity is completely different essentially. And people are normally getting confused, it's the same. So they even confuse tie binding and phonons because when you solve it's very similar. You have the ion IKA and they forget even what they're solving. But actually they're completely different if you want to think.
Sorry, the number of bands, why does it have to depend whether the particles are fermions and bosons? Because in phonons we treat it as
these are not bands. You see, this is good when talking. These are not bands. These are normal modes.
Yeah.
And you can have like 10 excitations going in the same mode. If you are absorbing energy.
Yes.
They can all go in the same mode and absorb the same mode.
Yeah.
Yeah. What was the question?
You just mentioned that phonons are bosons.
Yes.
That's correct, but in this way we treated everything classically, so why,
yes.
does it?
I'm just saying it comes from the finite number. We have a finite number of modes here,
Yeah.
but yet you can excite as much as you want, and all the energy will go to the same mode, in difference to here. You can pack 2 electrons and that's it. Okay. So before we do the case which I mentioned yesterday, I would just like shortly to cover different masses, because I think it's kind of bad that you finish this course without encountering the case of different masses. So I would repeat the example from yesterday a bit faster, but really having 2 different masses inside. So because now I can plot them with the same distance. Mass 1, mass 2. This is A. And this is U1, and this is U2.
And it's not exactly in the middle, it's just somewhere.
It just, well, it's not important. The difference, the distance doesn't matter anywhere. So we can again write the Newton law in generic way. Let me first write for some mass mu has displacement mu alpha. Is there any more index? No. Mu is the index in the base, in the unit cell. How many atoms are in the unit cell? This is the index mu. And here it will be over all J, nu, and beta. This should be some atom N, no? I should call it some atom N. N minus J times the displacement mu JB. So I'll just call it N alpha. Okay, so N and J are indices in the lattice R. Alpha and beta are XYZ, and mu and mu are the indices in the base. Yeah. And the masses are not the same. So here I have to introduce the solution, but this time it has to depend on the mass. Mu alpha. Mu, and it will be 1 over m mu times I omega t I k. Sorry, this is n and a in 1D. So each atom in the base will have its own amplitude, but displacement will depend on the mass of that atom. The bigger is the mass, it will have smaller displacement.
Why the swirls do it?
That can be derived.
It should have a dimension of length, right? Displacement.
Maybe it's due to canonical momentum and stuff, but no.
Yeah, this is not any more displacement. This is the, you're ruining the, this is a different variable. It can be actually derived just from the D's, just from the dynamical matrix. But this is a bit easier way to come to there. But yes, this is not a normal displacement. It can be. It's just kind of scaled by the mass. Then let's plug this inside. Minus m mu omega squared 1 over m mu u mu. E under I, K, and A is equal. I'm not writing the part of I omega t. J mu beta. Alpha beta. Times u mu and mu times E under I, K, J, A. So here we actually have a square root of m mu. We can divide by the square root of m mu. We will get, change the signs. We're getting displacement mu, amplitude, omega squared is equal to the sum of J mu beta Rn minus Rj times displacement mu divided by m mu and mu I k. Well, I could have used here Rj. This was just 1D Rn. I think a bit 1D, a bit general. That's correct. Let's write this here. Yeah, I was missing here alpha, sorry, and here beta. Because I have to define in which direction the atom is moving. Yeah, so, okay. And then this can be written as mu beta And the new dynamical mass dynamical coefficient matrix is defined with the masses. Dynamical matrix. So everything is scaled by the masses. This is maybe the easiest approach to solve for different masses. And we see that in this case, the problem has dimensions of number of atoms times the number of basis atoms times the number of dimensions. It's quite large. But if you know the dynamical matrix, you're reducing the problem. We can go from the middle. Okay? So let's try to solve this one as quickly as possible. This will give you many possibilities for problems to solve, because with the same mass we can solve only these many problems. So M1 times displacement U1. We have only one direction. Is equal minus T0. I'm putting right away on the same cell. Okay, this is the cell N, U1. Now these two spring constants are the same. I don't need to put them different. No? Atom A, atom B, atom A, atom B. I can call them K, whatever. I can again define them positive, also negative here, like minus K, so I put them in plus K here. If you're going to do something of this type, tell me, write it in the problem that it's clear what you're doing, that you want to have positive sign, that you are defining them negative, and if you will use this trick in the exam. Okay, the first neighbor is U2, and the neighbor from before, it's U1 from N minus 1. And for the mass 2, this one is the UN in the first cell, in the same cell. U1. No, here was 1 and 2. And 2, this should be 2. Here is 1 of the cell N plus 1. So D0 is equal to K. This you see right away already. And we can write M omega squared U1 minus 2K U1 plus K U2 plus K U2 minus RKA, and we can write it in a nice form, U1 minus 2K over M.
Sorry, doesn't the D0 has to go with a plus sign?
D0 is positive, always. The meaning of it.
Yeah, it was right in the derivative, yeah, okay.
Oh, I'm not sure. The force is this minus Fx, no? What you remember from minus 2K over M. I'm dividing by M. I can change the signs also. It's just an exercise for you actually. You can be doing it independently, we just compare results in the end, it's nothing smart. U2, this will be K, minus K over M minus K over M plus equals omega squared U1
The indices for M.
M1. I'm very used not to use the masses. And then for the second one, let me shorten it a bit. M2 omega squared U2 is equal, I'm changing the sign to K U2 minus K U1 minus K U1 E under IKA. So that U1 is equal minus M2 plus K over M2 IKA plus U2 matrix. Here is minus let me check if it's correct so far.
Okay, the indices of the
I made a mistake.
M1's in the top right
indices
in
of
this.
the N.
For the eigenvalue,
The indices in the matrix.
I made a mistake, just let me catch it. What was
no,
wrong?
it's not a mistake.
I'm saying I have different here. It's not so good to. Yes. I deleted the expression for the U. This is a big mistake. I'll have to change quite a bit. Yeah.
1 over square root.
1 over square root mass. Yes. So U1 has U1. Sorry. I forgot this part here. So I have to go back and introduce that guy. Yeah, it was somehow too simple. Sorry. Okay. So here we will, again we have, we divide by square root of M1. And we are getting M squared U1 equal to U1 times 2K over N1. That's correct. Plus U2 minus over n1, n2 plus k over square root of m1, m2. Okay, this is one. And here we had similar thing, m2, m2, m1, m1. So I will get omega square u2 is equal u1 minus k over n1 first one would be k over n1, n2, 1 plus minus minus, here is okay, let me check now, and of course
Should it be a k?
sorry? K minus. Okay. Now we can proceed to solve this one the same way we did yesterday. In the case it's K0 and then the edges. But actually, I mean, you can really solve this completely. We can attempt that just to change a bit from the yesterday's derivation. It's not so difficult after all. So you have 2k over n1. Maybe I'll just give a solution at some point. Other things are more important maybe. Minus k squared. So here we have terms 1, but 1 is 1 times 1, and this also gives 1, and then we get a mixed term, e on the ika plus e on the minus ika, which gives 2 cosine ka. You see that? And we multiply these two brackets. Should be 2 plus 2 cosine ka. Is it correct? Please check also.
Shouldn't in the first line or not above?
Here?
Yes. Shouldn't it be m1, m2 inside with un, and then with u2 it should be just m2 without the square root?
Here you had the root of m2, and then we divide the whole equation by the square root of m2.
So with
This
u2
should be m2, right? This should be m2.
But then there is already m1 there because of u1.
Yeah, and you have m1, m2.
No, it's I think
Sorry. It was, so completely wrong. Sorry.
Yeah.
I was trying to be fast, but here it's correct. Yeah. Thank you. Yeah, because I switched the places. Yeah. So what do we have here? Omega under 4. Omega second. is a part when you multiply this times this, plus 4k squared, and 1 and 2. So this is this, minus this 2, plus this, and then this. So we can keep copying this. So here we have 4k squared and 1 and 2. Here we have 2 minus 2. So this will be plus 2k squared and 1 and 2 times 1 minus cosine k. Correct? You checking? And we can just solve for the omega squared minus b so this squared 4k squared and 1 and 2 squared and then m1 squared plus m2 squared plus 2m1 and 2 minus 4 times, which will be 8 k squared and 1 and 2 we can go in the right direction. Okay, we can factor out this one. Let me just check.
It's 2a.
Sorry?
A
This
is 1.
last one.
A is 1.
A is 1.
Yes.
So 2 and 2 I can divide. I'm trying to be fast and it's actually quite dangerous. 1/2. I'm going to factor out m1 and 2 and k and 2k. What I have left is m1 squared plus m2 squared plus 2m1 m2. So this is this part. Here I factored out the square root, so I have to multiply by the m1, m2. K is out.
Twice.
2 is left, no? Is it correct?
Yeah.
So this and this cancel. It's supposed to be very, very fast. If I don't go through all the steps, but then I make a mistake. So omega 1, 2 is equal. I can write this also with m1 and 2, k m1 plus m2. 2 and 2 cancel. Plus minus K on M1, M2. Minus 2 M1, M2 cosine Ka. I think that's correct. Plus. I think, let's see. M1 plus M2 squared. Okay. So this is the dispersion we are getting. And you can analyze the same way we did yesterday, just from here, from the solution. For K0, you will again have solution. So this is, if this gives 1, this is exactly M1 plus M2 squared. So it gives. And then you will just have M1 plus M2. You will have, when the minus sign is here, you will have 0, and you will have M1 plus M2. So it will be 2K M1 plus M2. Yeah. And at the edges, you will have pi minus, you will have once 2K over M1, well depends, 2K over M2, depends which one is larger. You will, if you take this ring 0, you will get it, so you get very similar, same shape essentially, like yesterday. Which is actually, can be expected that if you change the springs or you change the masses, it's the same type of behavior. I mean, it won't be same to every detail, I mean, to every angle, but. Okay, so now we can do different masses as well. I mean, this was largely just mathematical exercise, not much new physics involved. You can go back and look for the eigenfunctions, but we already put it as an ansatz that they'll be scaled by the mass. Okay. Now let's go to the problem of the next nearest neighbors. You still copying?
Sorry,
Yes.
I really don't understand why did we choose this 1 over square root of m, because it changes this.
It's a scaling. It's an ansatz. You can prove it. I did not go through that in preparation to make it. Intuitively, it should depend. No, this is a very intuitive thing. So it's just a scaled displacement.
Yeah, but we know it will depend on the mass, but how does it depend exactly? The square root dependence. How can you think about the square root dependence?
Okay, I can. It's coming from a different derivation. Now I have to remember how to come from there. But this is used as an ansatz. Okay, next time we can discuss a bit more.
Yes, I kind of asked the same question. I think if we started the derivation the same way we did before without introducing n, we'll reach the same answer.
If you did what?
If we didn't introduce square root m inside u.
Yes, I think it should come out. I just don't remember. Yeah, I think it should come out.
I tried it yesterday.
Really?
Yes.
Okay.
But then why, how can we use this m? I mean, if it comes in this 2 ways, that one is easier. How do we use it another way?
This is from the beginning to know what you have. It's not difficult, I just don't remember how it comes out exactly now. To answer Edward's question. So I will just go through it and show it. Hopefully.
Do we use the dynamical matrix in some way?
Yes.
How?
Yes.
What do we
Well, you can just do it that you don't go from the force constant. You go from the dynamical, but then you have to know the values. You have to have given the values, and then you can just say that omega squared m is equal to dynamical matrix times displacement. That was the one so it is much easier if you know the dynamical matrix. It's half the way to the solution. If it's given in a problem or if you know, it's a big help.
Mathematically, it can be seen that if we choose the square root of m1 and square root of m2 to define this u1 and u2,
Yes.
then this matrix, this big matrix, is Hermitian matrix, and the eigenvalues are real.
It is not just symmetry requirement, it is, it really comes exactly.
Oh.
Yes, but let me just, I didn't review enough to remember it. It can come from something. Okay, this is different masses. Now the second neighbors. You tried? Okay, good. Anyone who would like to come on the blackboard? Three? No, because you weren't here. You're so enthusiastic. I have a hard time choosing. Okay. Do you mind if you turn off? Is there somebody who is not shy of camera? Because actually it is not, if you want to review later. Are you shy of camera? Just come, I mean, it's, anyway, it's for you guys. I don't think people are watching in general. Why are you so shy?
I just don't like.
I mean, for other people to review later, it's better to have
And
it.
actually, when I am rewatching the videos, I hate hearing my voice.
Yes.
I know, I have the same thing there. I don't watch my videos, that is solution. I agree. Because we hear our voice differently in our head. What you hear is like what others hear, actually. So what do we have? Okay, maybe I can also do something. I can draw the, we have the case of the second neighbors. So this is atom n plus 1, n plus 2. Let's call, no, there is force constant d0, d of a, d of 2a, then d of minus a, and d of minus 2a. Okay, so let's start from, we can do from the integration. So we have just one atom in the cell. Okay, if you have derivative, then you have
So
so all one on the left.
UCI omega t UCI
So you're already plugging in the
and
second derivative. For the
and this is here. This is un, and it have itself. So we have d0.
It has to come with minus, no? The Newton law comes minus the ij, no?
I'm very confused about the signs.
This is the Newton law.
Okay.
This is minus d0 times its own displacement, u1.
K and A, and then minus.
Here we really want to talk about the signs, so we are not going to play with the signs.
U is the same because we have the same.
D1 is d of a, no?
Yes.
Okay. We can whatever, I mean, just to.
But then U is the same thing. We don't need to say U1 and U2.
Yeah, because we have just electrons. So
Yes.
it is a
We don't.
monatomic linear chain. I can write it.
This IWT, and now we are thinking of this one. So it should be K and this one. Minus D2. D of, okay, if we call this D of A, that one should be D of minus A.
Yeah.
But eventually it's the
Yeah,
same as
yeah,
TOK.
good. Okay, but it's okay to write it in for once.
Okay.
Whatever,
Then-
it's okay. I'm not sure.
And it is
How much time you have?
T, K, and this is -1 minus D A. Again.
Oh, yes, I forgot.
T is 10 plus 2 AK 2 again 2 into I omega T e to I K and n minus 2 this time K.
N minus 2.
N minus 2 and then A. And then we don't need the n and we don't need this one because it is everywhere. Yes, there is U.
Yeah, but U is also the same.
Yeah,
It becomes trivial in this case.
Yeah. But yeah, I can. Yes, we can take it, but it is.
Yeah, sure. I mean, yeah,
I don't
only
like to
if you
take it
have more
because it
than
is-
one dimension or more than one atom in the unit cell. Then you need to keep it, otherwise.
Then we know that D0 is these two dA
Okay,
two.
this is correct if we play with the signs, but here we have the signs as, so, okay, you can write it like this.
Okay.
And you have a minus sign. D0 will be minus 2D.
So we don't play with the signs.
No, let's just derive the conditions. So let's have the simplest case, because we have to actually derive minus 2.
Yes, because we need -1 there.
So this has to be larger than 0. This is our first condition. Okay, let's keep it, let's not erase it there.
And then we change the sign. So we'll have this minus with this stay, but everything will come positive. So we'll have m omega square equal. We can take 2dA out. Then here we will have we have this one with negative sign and this one with positive sign. These two give 2 cosine
Yeah, but she's changing sign in the whole equation.
AK.
Yeah, a few things going on. It's
And
recipe
these
for
two-
mistake, as I proved a few minutes ago.
Cosine 2 cosine 2Ka. Then here we will have 2dA out, and then we'll have cosine. Then let us make this 4. No,
No,
let us
2.
skip 2 minus 1
Okay.
plus
Why minus 1?
because now
We
this
change
one
the
have
sign.
negative sign, right? If we will have this
Okay,
one
okay, right, okay. Good.
plus then this one 2 d 2a, and we'll have again 2 cosine 2ka minus this minus 1. And this is cosine square 2ka,
Sine.
ka, sine square ka over 2. So this is 2 plus 2d of 2a multiplied by sine square k.
Isn't it minus?
Minus.
This is 1 minus.
Yes.
Mhm.
So if
Also
we take,
here. So here we have.
can we take everything here and divide by m, and we call this omega square.
Okay.
I think it should be 4.
No, wait a minute.
It should be 4.
Yeah. If it's a little bit different, it's much more difficult to check. Yeah, it should be 4. It should be 4. It should be 4.
Yes, because this is 2 sine square.
Yeah.
And the minus in front?
Yeah, is it? Is
yes,
it minus?
yes, it's correct. It's correct.
Yeah, because then.
Yes. And then to make it in the easier form to analyze, to get conditions of this form, and for me to be able to check, let's factor out this part. D of A sine square Ka half.
Okay.
I mean, it can be done in a few ways, but yeah, we just continue with omega squared is equal
So
minus 4d0, dA
sine square Ka over 2. And then we will have 1, 2. Yes. Yes.
and this can be taken as sine of 2Ka half times cosine 2Ka half. No, as a double angle, it can be expanded.
Ka.
No, sorry.
Sine Ka over 2.
Sine squared 2Ka is equal 4 sine Ka half cosine Ka half, okay? Right?
Okay.
Squared.
Then this one would
And you're factoring out this.
there, yes. I
So
will
you have a 4 left.
Cosine square Ka over 2.
So we can actually put it.
We divide,
It's
we
easier.
don't divide.
D of A.
Yeah.
Oh, sorry, no, it's a bit squeezed inside. D of A plus this times D of 2A.
Yes.
4, okay. D of 2A, and there is times 4, so
There is what?
4.
Yes.
Because you already had 4, and then you got a new 4.
Now we need to plot this.
See?
When K is 0,
Okay.
everything is 0.
Okay, no. Before plotting, we should get the condition. So we can call this first condition. Conditions are based on we want to have positive frequency. We will analyze today what happens when the frequency is not positive. It was enough you're saying. No, do you mind staying?
It's okay.
It's okay. Okay, good. So to have omega squared positive, and here it's a minus in front, this has to be negative in all the cases.
Huh.
Okay. Here we have cosine k. In principle, this can get a value of 0. This should be always positive. This bracket. So in the case when this is 0, d of a alone should be negative, no? So the second condition, d of a should be negative. And then the maximum value of this cosine is 1. So we can write the third condition that dA plus 4 d of 2a should be negative. Do you agree?
Okay.
This is like the maximum value of the cosine. Okay, now we should solve, we have 3 conditions, inequalities. We should find the range of allowed dA and d of 2a, because obviously not any value is allowed. It brings to negative frequencies. So do you have chalk or?
Yes, this thing. More space.
So I would advise that we draw to it graphically. It's the most intuitive.
Let's just put them so we can see them. When we have d naught is equal to minus 2dA minus 2d2A, and this should be greater than 0. And the second one is dA is less than 0, and the third one is...
So it's a pretty stupid question, but the condition number 2, does it say that d of A has to be strictly negative, or can it also be equal to 0?
0 is fine.
Yeah, it's fine.
I mean, you can have acoustic frequency 0, no?
Yeah.
2A.
Okay. This is what you...
Yeah.
I didn't... yeah, you're right.
But in that way, if we take d of A equal to 0, then it means that we have a one long chain, and the next nearest neighbors are coupled. So it means that we have two chains.
Essentially.
But why is the dispersion
Essentially,
cosine and not sine? Because in that case,
So, why is it cosine? You can come to the sine, I think, from there. Okay, so let's go
This
solve
one
it.
is 0, it means this one have to be negative, right?
Yeah.
Because this one is positive and this one is positive.
Now, let me just, I feel more confident doing this. This is for sure good physics. I'm not sure. So let's go with the, which one? Maybe this one is the easiest.
So dA is negative.
Yeah, so let's,
So we can only start from here. This one is not relevant.
you want to, there are two ways. You can color the allowed or color the forbidden range, so that what is not colored remains allowed. When you have three conditions, maybe it's easier to leave untouched the good one. Now you understand.
Yeah.
So if d of A has to be negative, this is band, no?
Yes. Yeah.
Like that, no? So what we don't color, it means it's allowed. Okay. What is
And
this
do you know
condition?
that?
We can write in terms of
yes.
2 of A,
Yes.
d of 2A.
Let's see. D of A is
Actually, no, opposite, d of 2A, because it's like y of x. The way we are drawing, it's easier. That's why, you know? We are drawing this as y and this as x. So it's easier if you express d of 2 of A, how it depends. I mean, it can be done either way.
okay. So d of 2A is, we can put this one with negative sign, less than minus d of A divided by 4.
Yes.
So
Let's draw that.
minus d of A is positive, right?
No, we just draw for d of A as it's drawn here. So for d of A having value of 1, it will be 1/4, minus 1/4. So it will be here. No? For the value of 4, this equals 4, will be minus 1. Okay, for minus, so you can draw a line, which is very hard to draw. Oops, so go through 0. Roughly goes through 0 now. And it has to be smaller than the line.
So it should be in this region.
This
so
is
that
good,
this
yes,
one
yes,
is not,
yes,
not
yeah.
allowed.
Yeah.
Okay.
And the first condition,
So d0 is some positive number that we don't know.
this is the
We know
first
that.
condition, number 1.
So assuming d0 is 0.
No, this 0 has to be positive. Then this part here has to be positive. When you change the sign, has to be less than 0. Removing the 2 is not important. So d of 2A should be smaller than d of A. So this is like a line of this type. Oops, I'm really drawing terrible today. Yeah, this one wasn't so bad. And this is not giving a new condition, you see, because it's already in the forbidden region. So we managed to find here. Oops, I'm reducing further and further. This is allowed range of dA and d of 2a. I mean, it's important that you understand what we are doing and what happens if you don't take the right limit. Okay, so let me draw. Here is our final. Okay, let me go from there then. This is the dispersion that we derived. Ka half. So that's good. So if you plot it in some plotting program, for omega, not for omega squared, you will get something of this type. I'm not able to draw it very nicely. Oh, not symmetric, not good. And this bump here is completely due to d of 2a. When you set d2 of a 0, you will get what you've seen so far. So this is the effect of d2a. Here it's really drawn already.
Do
Is
we
it,
want it?
Is
Is it stable like this?
This is okay. You're observing like, okay, I will talk. This is okay. This is
Is
not
it
wrong.
bumped at k equals pi over 2a?
I don't think, no, I don't think it's in the middle. Oh. Okay, let me see the next case. When d2a is exactly minus 1/4 of d of a. So the frequency is minus 4 sin square k and half times d of a 1 minus cosine square k and half, which is a sine square, 2 of them, minus 8 d of a sine on the power of 4 k a half.
In the first step, we didn't apply any condition, right?
In the first?
We didn't apply any condition here.
No, just plotting it. Just to understand. So if you're just at the limit, we will get we still plot omega. It will be sine squared. So what it has, it's a much shallower dependence around 0. This is like sine squared.
Not a linear at k equals 0.
No, because square, no?
K square.
And now I will go just a little bit in the band range. So the other way is this line. It's this line now. Then we go just a little bit above. Un delta. So the frequency is equal minus 4 sine square Ka half d of A minus 1 cosine square Ka half plus d times 4 cosine square Ka half.
We need d of A in the first cosine.
Yes, yes, yes.
In the first cosine.
Yeah. So I will have d of A 1 minus cosine square is a sine square. So I'm getting d of A sine square Ka half. And here I'm getting. Okay, I'm just copying for the moment. So here let's write the whole thing together. Minus 4 d of A sine on the power of 4 Ka half. And here we have 4 times 4 sine square Ka cosine.
We are missing a term. We need 8 times of d of A sine to the power of 4.
No, we are getting, no, I write sine square of Ka.
d sine square k.
No, here there is no d. This is just
From the second line,
here.
if we take delta equals to 0, it should reduce to the first equation. To this one.
The delta.
To this one.
Yeah.
Yes, I agree.
So there is 8 there is 4 there.
Ah,
It should be 8 also.
yeah, right. Here it's 1 minus.
Twice, yeah.
Ah, 8, right. Minus, here it's 4 delta here. Is it right?
Yeah.
Check. Yes. So this is the first one that we plotted here. Oops. I need to shift a bit. So, this curve is this one because d of A is negative. So this is minus 8d of A sine power 4k half. And now we have a negative contribution with the Ka, with the delta which is small. But this is completely negative. It will be something on this side. No? Roughly. With the delta amplitude. So we are introducing something in the negative frequency, and when we add up the two, we'll get something like this. We'll have a small part of dispersion which actually goes negative. And this we can actually, okay, this is plot for omega squared, which you can do also if you plot the sine and if you just take a square root of everything. Should I repeat for omega squared, this plot? Because here was still omega. I can do the same thing for omega squared, because I don't want to have omega. It has to be complex. I don't have a complex plane here. So it's easier for me to plot omega squared going negative. But, the same behavior. Okay, so what does this mean? Omega squared less than 0?
Not allowed. Not allowed.
But what happens? It can happen.
Dissipates in the system.
So if you plot, if you say that omega is equal alpha plus I beta, imaginary beta, and I have my displacements are proportional to E I omega t. What will I get? So it depends. If the beta is positive, I'm just getting oscillation which is damping, which is fine. But if beta is positive, it's becoming stronger and stronger, the oscillation. And it's unharmonic or melting. It's structural phase transition occurs through these things also. Some phone mode goes crazy, and until it reaches a new phase. So that can be indication also of the structural phase transition. But actually it can occur, and it happens that that once you displace it's a slightly different discussion than this. Once you displace the atoms from the equilibrium position, the restoring force is not able to bring them forward because they form a dipole moment. And this dipole moment lowers the energy so much that the restoring force is not strong enough to bring the atom in the... So this kind of processes that you actually go in the slightly negative path can freeze ferroelectric structure. One of the typical ones is barium titanate, cubic structure, I think, which has barium atoms on the corners and octahedron of oxygens, while in the very center is the titanium. And due to some of these vibrations, you will displace titanium out of the plane and in one direction, and the barium in the opposite direction, and it will freeze there. It will become a new ground state. So this is the ferroelectric behavior. There are different kinds of. There is also a case when, due to some changes or even heating, that you are reducing the frequency to lower one. This is called softening, or under pressure. It's called softening of the phonons, and it's also an instability that can occur. So displacive, structural, elastic, all of them are instabilities, and they actually occur. We can find plots with negative phonon frequencies. It's great. Anything else I wanted to say?
The softening happens when beta is negative.
When beta is negative, yeah, it can actually lead to sorry?
It's increasing in time.
Yes, it will go crazy, but it can be like a transient part to reach a new structural phase. I mean, it has to start moving, and then it reaches a new phase, and things change. Okay. Any questions on this?
We achieved this plot, the negative frequency,
Yes.
by changing the spring constant up to with
In
the
the
decontamination
region, yes.
to the forbidden region.
Yes.
So physically, what are we doing to the crystal that changes the spring
Many things can
constant?
happen. Many things. We can put under pressure. Or you can, heating is less likely, but it's possible. Or yes, for example, heating when you are close to some structural phase transition that it cannot be allowed. Or
So basically, it's due to some external.
Actually, if we will start to heat the crystal, we have these three atoms. This is the first neighbor, and the coupling constant or whatever is dA, this is dOA. If the temperature is big enough, this point, I don't know if I'm correct or not, this point vibrates with a big amplitude, and can it be said that the coupling constant between these two atoms and these two atoms become of the same order? Can it be said in that way?
well, they're all having the same amplitude.
Yeah.
I mean, it's always a combination of all the motions. It's just that the origin, I mean, still the sum, it's you superpose all the motions.
Another question. We solve this with just the atoms. The system is just composed of the atoms themselves. We get this solution for the forbidden region. If you said we heat it, we put pressure on the crystal. But in that sense, the Newton's equation of motion will have an added value for external forces.
Well, it doesn't have to be. It will just have a new equilibrium. You will not be able to expand. I mean, one of the things you would have a different R0.
Yeah.
So everything would be contracted.
Yeah, because I can imagine, because we put like d of A plus some small perturbation.
And also the D's are changing greatly. Under the pressure, you will change the force constant. They cannot move as easily if you pressure the system. They are harder to move, so they will reduce. So you're changing completely the physics. From the first, I mean, the equilibrium is changing, the D is changing. It's It's not just.
If we are compressing the crystal, the T has to rise or smaller.
And I was just going to say a few words about, is any of you interested in experiments? Yeah, it's interesting, good. I mean, it's not common here, unfortunately, and I think it's a big loss.
Yeah, we are talking about crystals. I want to see a crystal.
But we are covering very, very little in this program about experimental techniques. So I don't have time now, actually the time is fast, but I'll just mention 2 techniques in 5 minutes. How you can measure the phonons. You can use, actually we were talking with Misha that we will try to organize that you go to Electra during winter, maybe better than before the diploma or the thesis. So then hopefully you'll be able to see and ask many questions. So the idea is that you send all particles or radiation on the crystal, which then somehow interacts with the phonons or absorbs or excites them in the crystal. And then you see the change or to the particles or to the radiation coming out. The only particles which can be sent are neutrons. They don't interact with electrons. They can pass because they are very small and the nuclei occupying, I think it was the 10 to the 15th part of the cell, something so tiny. So there is not too much interactions. They will just interact with the vibrational modes. The energy of neutrons, 1 to 2 eV, and they're quite an expensive source. It's not the cheapest experiment you can do. So, inelastic neutron scattering. What does inelastic mean? Inelastic, you will hear it all the time.
The energy doesn't all transfer to kinetic energy.
Okay, yes, that part of the energy. The neutrons itself won't have energy conserved, but of course in the system the energy is conserved. So the initial neutron has energy E and momentum P. This is initial, and the outgoing. So initial, outgoing neutron, and the energy is of course conserved. Now it can be 2 cases. I'm considering that you only excite or absorb a single photon, which is not the rule. You can actually do it. You can excite many of them, 2 or many phonons. So this is a bit more difficult to analyze, but you see the sharpness of the peaks and experimentalist ways. I'm just giving the bare idea of the method, considering only 1 phonon. So what happens here, this is the final energy, is larger than what was sent in. It means that 1 phonon energy was absorbed. And if it's smaller, it is excitation. And the momentum I don't think I took into account the G vectors. In principle it can be. So if this is a phonon K vector, it's called Q sometimes, it depends. But you always have to take into account G, because this is big enough. So this is the case when the P prime is larger, it's absorption. And when it's smaller, this is plus minus essentially, which makes it a bit difficult to analyze. And the emission. And you can write it, excitation or emission, whatever you want. Well, that's fine. And you can write the energy in terms of the momentum. Is it important? Yeah, I think this is already enough. You can write the energy in terms of this, but it's the same thing. So this is the neutrons, and you can do the same thing with X-rays, with optical light. I'm not sure I have the time. If you send the optical light, it's normally a laser or something. You can also excite or absorb. But the difference there that you have such small, the light you're sending is around EVs. Okay, so the, how do they call, optical measure. It can be Raman scattering, which is mostly used for optical phonons, or brilliant scattering. For acoustic. Just that you send a light in the crystal, it actually refracts. There is an index of refraction which changes, so you don't have just momentum, you have N, and I'm calling it Q for the light. So the one entering, it goes up NQ initial and Q final, and it can emit or absorb a phonon. This is the whole story. So this will be final, is NQ, plus minus HK, and here it is too small altogether. It cannot excite and equalize this momentum. So it has to be within these limits. And you can actually find Q is much larger than K, because the energy of the light entering is the EVs, a couple of EVs, while the phonon frequencies, energies are much lower. It's at most 0.01, but it's usually smaller, it's millieVs. Phonons, much, much smaller. This is maximum. This is always smaller than this. And that would allow you to actually draw this as the initial photon and the one which is, I can draw them of equal length because the change is almost non-existent. And this is the phonon wave vector, which is much smaller. This is not drawn to the edge. And being the same, I can easily, from the height, and the angle, I can estimate the two. I say K is equal sine of 1/2 theta times NQ. Well, this is just the absolute value. And this is the way I can get the one wave vector from the Raman scattering. This is just idea that you will hopefully get developed more, how to get anything in experiment. This is just very short. Of course, all these peaks are smeared when you read an experimental data. You won't get nice peaks at all. You will get something like a mess. There is a background scattering, which is like this big. And then they're trying for this, attracting the background, trying to come to the peaks for the certain phonon frequencies, where they can be. And this was very, very rough, just to get an idea. Any questions? If not, well, what's the time? We can maybe solve something.
I would ask something about the exam.
Oh, yes.
Would it be like we have the midterm was on one part? Would it have kind of reduced, like would we have as questions from both parts? Or
From both parts. On Thursday we will do like one example midterm. I mean,
This Thursday.
no, midterm, sorry, final. Today is not my day. Huh?
This Thursday.
This Thursday. It's the first, and then there is next Thursday the second tutorial. I would say it's close to half-half, maybe a little bit less on the first part, but 40-60, because the midterm is entering very with a small weight. It's mostly for you to realize where you stand, how things are. So we cannot put the big weight on the second part because it's still the grade is coming from the final. Yeah, we'll see. But it's similar time. 2 problems, and you choose what you want to solve.
And 20 questions for the multiple choice.
Yes, 20 quiz questions and 10 points on the problem. So it isn't bigger, it's a longer problem.
We choose one of the
You
two,
choose one little problem.
and it's 10 marks.
Yes.
And 3 hours or 2.
But it depends a bit on I go through the exam and see how long it takes me to solve it. Sometimes it's more writing. Some really require more time, but I don't think the time is an issue usually. Maybe for one of you the time is an issue. What I have experienced is not the time usually. Unless you really completely confuse something and you spend 1 hour doing it wrong, something, then maybe, but usually it's not the time which is a problem. Yeah, so shall we try to solve the effective mass problem? Yeah, let me give you, because once I forgot to give you, I had it with me and I didn't give you. So, for Thursday, if you can solve this problem, this is an important one to understand the motion in 2D. It is not too difficult, you just have to separate motion in x and y. Write the separate equations, how it moves along x, how it moves along y. So this I hope to solve on Thursday. And then I'm giving who has time. This is probably going to be for the next week, and you might not even have time because both of them are a bit more advanced than so this one, please, everybody try to solve. This one, it's more optional. It's not. Maybe we can solve some more basic ones from before what I gave you. We could try that on Thursday. Depends how much time we have after solving the final exam. One example of the final. Yeah, it's number 2. On this one, there is no number 1. I just realized I kept the 2. So, would you like to solve the effective mass problem? Remember the one we discussed a bit yesterday? Or you have a lecture. I mean, this, yeah, it's 47. Yeah, they fixed it at the clock. You have a, when you want to go, whatever you prefer.
I'll just try the effective mass profile.
You want to try on the button? Come, come. I'm very happy to see
What-
volunteers.
What number? The first?
It was number 2 in the sheet I gave. I sent my Nadia. Yes, yes, yes. Oh.
Beautiful.
Don't have to. Here is the problem.
The recording.
Ah, sorry.
So it's